Good morning, everybody. Thank you for joining this e-café. So we'll have a first presentation phase by Laura and Franz that you can see on camera. Please turn off the microphone during the presentation phase. You can ask questions in the chat, but you can also open your mics and cameras afterwards to ask directly your questions. Raise your hands, of course. So the whole idea is of this e-café is to, of course, get some insights from the presentation, be able to ask your questions. But after the presentation, we'll have also a networking session, a short networking session. So the idea is to meet other participants that are interested by the topic, maybe exchange email addresses, make further appointments, etc., etc. So this is the second session of our e-cafés that we are hosting. And the whole idea is we've targeted the Fridays from 11 to 12, so that it's the day people are more relaxed and less stressed by the deadlines, hopefully. And the idea is really to get a kind of an informal conversation at a cafe, so don't hesitate to raise your hands. I hope we'll solve in the meantime the cameras authorization and micro authorization, because you should get it for the networking, of course. So yeah, the agenda is welcome and introduction. Then Laura will present the Push to It project, and Friends, that is part of the Push to It project, will present sustainable process heating technology and the first references. So this should last till 11:30, a little longer maybe, and then we'll do a little networking. Hopefully we'll solve the camera micros by then. Yeah, just a short introduction for those who don't know Alliance ALLICE. We were created to federate and innovate to decarbonize industry. So we are an industrial alliance who gathers all the value chain of industry decarbonization, from the solution providers to the manufacturers, but also with all the value chains, so the financiers, the prescribers, the utility managers, etc., etc. We cover all the levers to industry decarbonization, which is the first one, the main one that we push towards is first, as an industrial, do the energy efficiency measures on your site, and then switch. The second lever would be to integrate alternative energies, electrification, and of course high temperature heat pumps in general are in this second lever, integration of alternative energies. And I will not detail all the other levers, but they are in this small scheme. And well, in short, what we do is we produce collective studies for our members so that they can have independent reports, data, and studies to be able to make the right choices or decisions on their industrial facility or site. And also for solution providers, it helps to know the other solution providers' solutions and the complementarities, the synergies in general. And yes, for the slides, they can be shared afterwards. Yeah, and I've been, just one last word maybe about our activities. We are also having coordination of the network, promoting the decarbonization sector. So this is a little bit what we're doing with the e-café, trying to make connections between the good persons, the experts from a topic, and maybe the people interested to know more about the technologies and these thematics. Okay, so I just very briefly, since we'll discuss about the high temperature heat pump topic, and Laura will go more in detail and Franz afterwards, but you must know, or you should know, that the IEA heat pump TCP, so this is the link here displayed on the slide, contains a lot of resources, and especially the Annex 55 relates to high temperature heat pumps, so you can make sure to consult it afterwards, after the meeting. And we have also this map that we've produced in one of our studies that is showcasing all the different projects, locations, and solutions being tested or almost in operation, actually, on industrial facilities. And maybe Laura and Franz will complete. I will now let you, Laura, continue, and you can take the control to switch the slides.
Okay, thank you very much for the introduction. I took the control. Okay. Hi, everyone. I am Laura. I am a researcher in Tecnalia Research and Innovation. This is a technological center located in the north of Spain, and my main activity or focus is in the area of thermal energy systems. Tecnalia is coordinating push-to-heat project, and this project is focused on heat upgrade technologies, mainly high-temperature heat pumps. And now I will give you an overview of the objectives of the project and its main activities. Okay, so first of all, which is the context and what motivates a push-to-heat project? Well, decarbonization of the industry, as you know, a huge challenge, and it's kind of urgent. So we could say there are many different approaches for reaching decarbonization in the industry, depending on the processes and sectors. But here, just showing different strategies that can be used for the decarbonization, such as energy efficiency, electrification, integration of renewable energies, the use of the alternative fuels, and even capture carbon capture and use in certain processes. So within these decarbonization strategies, high-temperature heat pumps are identified as a key player for the decarbonization of industrial heat. And we find this as a key player for, as I said, for decarbonization, as they can harness waste heat coming either within the processes themselves, inside the industry, or from external resources or waste heat sources. And these technologies upgrade the heat to a higher temperature level useful in the industry. Okay, the market potential of heat upgrade technologies is huge. It has been identified that around 37% of the process heat required by European industry is below 200 degrees, and this fits very well with these technologies. But also, at the same time, we have a huge amount of available waste heat between 40 and 100 degrees, which can fit very well as well with these technologies. So the highest potential is found in the food, paper, and chemical industry, but still the market is emerging. And this is why projects like Push to Heat, which are focused on the development of high-temperature heat pumps and the demonstration at a real scale in the industry, are very important for widening the installation and the proper integration of these technologies. Okay, so let's go now to Push to Heat project. Okay, we have on the one hand in this project technology-related objectives with the optimization of 4 different heat upgrade technologies. But not only that, we are also focusing on market and business-related objectives. We want to push forward the market potential by analyzing new business models and making actions towards these technologies' market deployment. And we will mainly do this among different kind of activities, but by demonstration of 4 full-scale pilot plants in different industrial applications. And here we show the waste heat sources temperature level range and heat supply level temperature levels, and also the address the heat upgrade capacities. Okay. But which are the technologies we are developing in this project? Okay, we have different kinds of high temperature heat pumps. On the one hand, we have the electrically driven heat pumps. And in this specific project, we have two different compression heat pumps, one by SPH, which will be demonstrated in demonstrator number 1. The second one by Canon Bono, which will be demonstrated in demonstrator number 2. And then we have, on the other hand, the thermally driven heat pumps. And among these kind of heat pumps, we can differentiate between the absorption heat transformer by BS Nova, which will be tackled in Demo 3, and also the thermochemical heat transformer by Kupinch, which will be addressed in Demo 4. Okay, all these technologies will provide steam for the industry, and in certain cases, we are using, combined with the heat pumps themselves, external steam pressure upgrade systems, such as thermocompressors or mechanical vapor compression systems. Okay. And now let's go to the demo sites themselves. Okay, the first demo site will be located in Germany, in Weissenburg, in a paper industry of Felscholler Group. This demo site includes a high temperature heat pump with piston compressors by SPH. This will be explained by Franz later, much better than me, but just briefly, this heat pump is using waste heat from the paper machine dryer and in a temperature level between 30 and 50 degrees, and it will produce steam directly in the condenser at 2.3 bar, around 123 degrees. The capacity is around 1.2 megawatt, and the expected COP, coefficient of performance, is 2.3. Okay, the second demonstrator of push to heat is addressing as well the paper industry. In this case, is located in Italy, in Quartiere di Guarcino. And this is a high temperature heat pump by Canon Bono, which is combined with a mechanical vapor recompression system to get higher pressure in the steam. Okay, in this case, the waste heat is taken from the cooling water of the cogeneration plant of the paper mill, around 85-90 degrees, and the high temperature heat pump will produce steam at 1.7 bar, around 115 degrees, and then this pressure will be upgraded by the mechanical vapor compression system until 6.5 bar, around 162 degrees. The expected capacity is around 850 kilowatt, and the COP of the combined system around 3. Okay, demonstrator number 3 of push to heat is located in the same paper mill as demonstrator number 2. So this paper mill in Italy will have 2 demonstrators at the same time. But in this case, this is addressing a thermally driven heat pump, an absorption heat transformer by BS Nova. The waste heat source is the same as in the demonstrator number 2, so the cooling water of the cogeneration plant. And in this case, the heat transformer will produce a steam at 3.3 bar externally with the use of a flash tank combined with this system. And then the pressure will be upgraded by using a thermocompression system. And this needs a high pressure steam stream coming from the plant. This is available in the plant. And the final pressure of the steam will be 6.5. So the same conditions as in the previous demo site. In this case, the upgraded heat capacity will be around 340 kilowatt. And in this case, we are not talking about an electrical COP. We are talking, we focus more on a thermal COP, which is around 0.5, and this is typical levels in thermally driven heat pumps. Okay, and finally, demonstrator number 4 is addressing a thermochemical heat pump by Kupinch. Qpins has a pilot plant scale system in the facilities, but they have also an integrated unit in a chemical plant, and this will be used for push-to-heat project, as the monitoring data of operation of this unit in the chemical plant will be used in order to widen the temperature levels which are typically used by this thermochemical system. They typically upgrade heat until higher temperature levels, but in this case they will widen the range to lower levels as well in order to address the objective temperature levels in push-to-heat. Okay, and this has been a very quick and brief introduction of the project, mainly focused on the demo sites. But if you wish to have more information, don't hesitate to visit the website. You can follow us on the social media. We usually post different information of the project, the advances, and you can find important information of the project there. And also, if you are interested in receiving periodic information on the progress of this project, you can join the stakeholder network, and you will receive biannual newsletters in your email. Also, we have an open call for experts if you wish to join the Push-to-Heat External Advisory Board. This is a board composed by external experts with whom we meet biannually normally. And we exchange different opinions, we got their feedback, and we share information. In brief, we are open to hear you, so any input, recommendation, ideas, needs, etc. are welcome, and I welcome you to interact with us, and you can provide also valuable feedback for the project. And this was all. Thank you very much.
Thank you very much, Laura, for the presentation. I saw there was a question in the Q&A panel. You can just feel free to ask your questions, but maybe we'll go with Franz's presentation, and afterwards we'll just open everyone can open the cameras and micro, and maybe raise their hands so that it's not a mess, but we're still a small group of people, so it's I believe it will be more friendly this way. And so I will leave you, Franz, maybe a follow-up, and then we'll do a joint Q&A session.
Okay. Good morning, everybody. Thanks for your time. Just a quick question. Can you see my screen?
Yes, we are on SPH company presentation slide.
Exactly, that's what I wanted to do. Yes, my name is Franz Helminger. I'm working for SPH as project manager, and will give you some insights, some information, basically of the history of this company. It's existing since 5 years, and then talking a little bit about our core technology, and then giving you some references, including the push-to-heat project. So the company was founded in 2020 by Mr. Hamacher and Mr. Mück, and then in parallel 2021 we have since 2021 an European family office investor, and parallel to that, and in 2022 they manufactured the compressor, heat pump, and test facility. And ongoing in 2023, there was an award from the German region, and also the first therm booster, which is the name of the product of the heat pump, was brought to the industry. 2024, the Spirax Group joined as strategic investor, and in 2025 we have around 10 units in operation, a little bit more than that. Very short, a little bit about the history of the company. To the core technology, so we are producing a patented piston compressor, high temperature piston compressor, which was developed for this ultra high temperature heat pumps with a very high efficiency, also in the partial loads, so with a good speed control of that. That includes in this high temperature heat pumps that the high temperature lift is normally needed compared to other heat pumps, and the compressor is optimized for high temperatures and for the synthetic and natural refrigerants which are needed for these high temperatures in this robust industrial design of more than 250 degrees in operation maximum. The next slide gives a little bit the same information than Laura already gave. So that's the principle of such a vapor compression heat pump. It addresses a little bit the temperatures our machines can address, but I will not go through all these details. In the center of the slide, you can see a basic design of our heat pump. So there we have, on the left-hand side, we have the evaporators, which are basically plate heat exchangers and some internal heat exchangers. We have our core technology, the compressor, connected to an electrical motor. And here we have a steam generator. It also represents a little bit how we name our heat pumps. It's based on the heat transfer fluid of the heat source side and also the heat sink side, and then the numbers of compressors. So in this case, we have an LS1, that means liquid and the heat at the heat source, steam at the heat sink, and with 1 compressors. And we manufacture up to 3 compressors on 1 heat pump frame, basically given here. And the higher the temperature lift from heat source to heat sink, the lower the COP, but with very low temperature lift, we have experience with COPs up to 7. As I said, the higher the temperature lift, the lower the COP, and typically is also by 2 or 2.3, like in the push to heat projects. I want to go through some references as the next step to show you a little bit how these heat pumps are used or designed, and also a little bit how they are combined. What you can see here, I limited the references, of course, to show you just the main things, the most important things. Here you have again this LS1 design in a 1 stage. In the first, and the test system, we used this 1233 ZD as refrigerant. We had around 85 degrees C at the inlet of the evaporator, going down to around 70. We generate steam at around 120 degrees C. And the same picture here with 1 compressor on 1 frame, you have around 500 kilowatts. And with this operating conditions, COP of around 4.4. The next slide, you will see a picture of it. So on the left-hand side here is the steam generator. Here, on the right-hand side, we have the plate heat exchanger. And on the other side of this picture, there is the compressor and the electrical motor. The next reference is an L2 we placed in 2023. 2 of them, it's also a 1-stage system with the 1233 ZD refrigerant, and with the operating conditions at the heat source of around 75 to 65, so inlet to outlet, generating heat up to 130 degrees C. And on the right-hand side, you can see the design of the heat pump with 2 compressors on the frame. And with these 2 compressors, you get up to around 1 megawatt and a COP of 4.4. Here you can see that on the left-hand side of the design, we have the evaporator and the internal heat exchangers, and in the center of the compressors, we have the condensers. And as I said, it's a liquid-to-liquid heat pump. As next, I will show you the graph of the design of the push-to-heat heat pump. There we decided, due to a higher temperature lift, so you can see here we have an inlet of around 46 and outlet 41 degrees C, and generating steam of around 2.2 bar absolute, so that around 120 to 123 degrees C. There is a higher temperature lift. Therefore, we decided to go to a two-stage, so that means two heat pumps connected to each other with two different refrigerants. So in the low temperature heat pump circuits, we have the R550E refrigerant, and at the high temperature circuit with our compressors, we have the 1233 again as a refrigerant. And yes, we are generating steam. So at the CAD model, you can see the screw compressors and the low temperature cycles. And on the right-hand side, you can see our compressors with the electrical motors and the steam generator. And we expect around 2.27 or 2.3 COP with a capacity of nearly 1.2 megawatts. And this heat pump is integrated in a container with all the ventilation on top. And on the next slide, you can see the container placed at Schöller in Weißenhorn. And there is one picture where you also can see a little bit inside of the container. It's not insulated there, but in the meantime, it's insulated. So the picture is from some month ago. And as you can see on the right-hand side, again, there is the steam generator where the steam leaves the container and all the other components from our circuits. I want to draw your attention to another project where we deliver two LS2, that means liquid to steam, with another refrigerant due to higher temperatures of the steam. So we are using there the 1336 MZZZ refrigerant and generating steam up to nearly 160 degrees C by using a heat source from inlet 92 to outlet 84. It's already very high inlet temperatures. And we end up to, for one machine, of around 700 kilowatts of heating capacity and a COP of 3. There again, now you know already a little bit the way we design it. So it's one frame with two compressors. Here you on the left-hand side again, the evaporators and internal heat exchangers. On the right-hand side there you can see a little bit the steam generator, which is a little bit smaller than in other projects due to the refrigerant. Finally, just very short, I want to show you another project. It's a research project where we combine steam generating heat pump from us using butane as a refrigerant, generating steam of around 150, 120 degrees C, and combine it in Vienna in Austria with a mechanical vapor recompression system to compress it up to 11 bars and 190, 195 degrees C at Takeda in Vienna. It's a natural refrigerant, as I said already, to generate steam and to go down to nearly 0% CO2 emissions for 7 months. As the heat source is not available the whole year, so it's limited to around 7, nearly 8 months of the year. Just give me a second. That's just the information again, but that's the same. That's it from my side. Thank you very much for your attention.